Thanks very much, Tom. Thanks for having me here and giving me the opportunity to tell you about this interesting topic. It started out, my interest started out in about 2003 in a paper with Frank Stillinger that was more asking fundamental questions about density fluctuations. And then as time has evolved, it's become apparent that it has connections to many, many different fields, and it even has practical implications, which I won't focus on. I'll focus more on the fundamental aspects today. And what I'm going to do is I'm going to give a survey talk. I'm not going to give a lot of detailed results. I just want to give you sort of a smorgasbord of the different kind of problems that are out there, connections to different areas, and yeah, and then of course if you have quick questions that you want to ask me during the talk, feel free. All right, so first, qualitative definition. A hyperuniform system. Let's see if I have this operating correctly. Whoops. What's the, nope. I'm looking for the laser pointer on this.
Maybe at the top, or there should be one there.
That's not working, but it's okay. Okay, hyperuniform many-particle system is one in which normalized, which I'll explain in a little while, normalized density fluctuations are completely suppressed at very large length scales. So what I'm gonna, yeah, thank you, analog.
The old-fashioned way.
Is that, what is the pointer on this?
It should be the red button above the, or below the arrows.
Nobody sees
Below the arrows.
Nobody sees the pointer anyway.
Okay, that's a good idea. Anyway, I'm assuming that everybody knows what a point set is or a point configuration. I'm assuming that people are going to be familiar with the idea of a lattice and periodic systems, right? So that's what I have in mind, and I'm thinking about systems like that in which normalized density fluctuations in some sense are completely suppressed at very large length scales, okay? All perfect crystals, periodic systems, and perfect quasi-crystals are hyperuniform. Hyperuniformity provides a unified means of categorizing and characterizing crystals, quasi-crystals, and special disordered patterns. All right, so let me just say a few words about this latter category of hyperuniformity. Disordered hyperuniform many-particle systems can be regarded to be new ideal states of disordered matter, in that they behave more like crystals or quasi-crystals in the manner in which they suppress large-scale density fluctuations, and yet are also like liquids and glass since they are statistically isotropic structures with no direct delta functions. They can exist as both equilibrium and non-equilibrium phases. They come in quantum mechanical and classical varieties, and they appear to be endowed with unique bulk physical properties. Now I'm going to stay away from this topic, but actually with Paul Steinhardt, we've used these ideas to create the first disordered photonic materials that have band gaps comparable in size to photonic crystals, which were thought not to be possible.
So you have random structures which have the properties
of a band gap.
Of crystalline.
Exactly, and it was, that's right, and very isotropic because these are disordered. Now I'm not going to say, if somebody wants at the end I can show a slide on this, but I'm not going to talk about this.
Now are you going to say more about what you mean by hyperuniformity?
Yes, absolutely, no, there's no question. Okay, so I'm going to go through a history of the problem to begin with, how I got interested. And actually Joel Leibowitz is the one who spurred my great interest in this subject. Okay, so he pointed me to these papers, I guess it was probably the early 2000, in which you have charge fluctuations within some finite sized window that grows like the window surface area. Very, very unusual. Now, at the time, I had been working on disordered sphere packings, jam packings. And we had, in a computer simulation, a structure factor that looked like this. And the interesting thing about the structure factor, which I will define in a little while, you can think of as just the Fourier transform of the pair correlation function. And the interesting thing about this was that this seemed to be going to 0 for small wave numbers, for very, very large length scales. For a random system, that's very, very weird behavior. Okay. Then I also was aware at the time of an observation that was made by Gabriele Joyce and Silo Slavini in 2002 about the Peebles-Harrison-Zeldovich spectrum for the density fluctuations in the early universe, which has a structure factor that goes to 0 linearly in K.
So that's just a Fourier structure factor, just a
Fourier transform.
Of the pair correlation.
Exactly.
But
Yeah.
density, I mean, this is not one-dimensional, so
No.
when you talk about pair correlation, you mean spatial pairs?
Spatial pairs, which I'm going to define in the next, well, 2 slides from now. Okay, so I'm going to be working primarily in Euclidean space, d-dimensional Euclidean space. And so you have 2 situations, an ordered set, infinite by the way, this is always infinite. An ordered set, a disordered set, you have a window, and I'm going to, for simplicity, make it a spherical window of radius r. And you can appreciate that if I take this window and I count at that position and I count the number of points within the window and then I move it to a different location, the number of points I'm going to register is going to differ. It's going to vary. So even for an ordered pattern, this is a random variable, the number of points within the window. So I can define a variance. A variance, so the average, of course, the average number within there is the number density, okay, times the volume of a sphere of radius r, which of course scales like r to the dimension. All right. And clearly, you're going to have a number variance for a disordered system. Now, if you have your typical Poisson point pattern, spatially uncorrelated, and many disordered point patterns, what do I mean by that? A typical liquid, or even a typical structural glass. The number variance will also have the same scaling as that for a Poisson point process. It grows like the volume of the window.
How big is R?
R, we're going to make R go to infinity. So this is an asymptotic result.
Well, then what the local density, relation between R and the local density. So it's like R, are we at the finest scale or just slightly bigger, or are we wanting?
Well, this is the overall number density is rho. And then I'm imagining a window which is going to be extremely large compared to the mean spacing between.
You're fixing rho to be whole
so
one,
you-
right?
I'm going to fix rho to be 1.
Okay.
Yeah, exactly.
Mean spacing also 1.
Yeah,
Okay.
yeah. And in fact, when you compare different,
So it's local, very local. It's interesting.
yes. But I'm also I'm thinking about what happens as this grows, as R becomes very, very large. Okay. Right. Now, we call point patterns whose variance grows more slowly than the volume hyperuniform. Now, I'm going to show you in a second that this implies that the structure factor has to go to 0 under certain situations as k goes to 0. Now, as I mentioned,
For you, anything that's whose variance is
Absolutely.
R to D is
exactly.
you
Yeah.
lost.
Absolutely. And Beck, I should mention, Beck showed for a spherical window that you can't grow any slower than r to the d minus 1. So then I'm going to answer your question.
Okay.
Yeah, Schmidt showed. Feedback improvement.
Oh, okay. I stand corrected. I thought Beck. He said Schmidt showed it first.
The lower bound of discrepancy is Schmidt, then Beck improvement.
Okay.
For spherical cap, that was the inside of Schmidt.
Okay.
Wolfgang Schmidt.
Now, as I said, all perfect crystals and many perfect quantum crystals are hyperuniform such that it grows like the surface area. Now, you can see this very intuitively, right? Because if you have an ordered system like this, all the fluctuations are concentrated near the interface. So it should grow like this. And it turns out a little more subtly, and I don't have a lot of time to describe this, but we actually have with Paul Steinhardt and company, we have some new results for quasicrystals. But many quasicrystals like Penrose will have this scaling.
Will there be others that have something in between?
Yes, I'm going to tell you. It's a great question. And I should mention that in 2002, Gabrielli and company called this hyperuniformity superhomogeneity. Now, all right, so just a few quick definitions. I'm thinking about a point process in d-dimensional space at number density rho. G2 is a non-negative radial function that is proportional to the probability density of having pair distances, distance r. The non-negative structure factor is just simply 1 plus rho times the Fourier transform of this quantity h, which is just G2 minus 1. Okay, and I'm going to denote the Fourier transform of that by h tilde. So that's the structure factor. Now, if you have a Poisson distribution, ideal gas, G2 is 1 for all r, so is S of k. If you have a typical liquid, a G2 that looks something like this, a structure factor that looks like this, and the important thing to note is that as k goes to 0, this is not going to 0. This is not 0. This is some positive number. That's very typical of a liquid. If you have a lattice, and I do an angular average, in the case of a lattice, then I have Dirac delta functions whose heights are going to be determined by how many points I find there. But you also have something similar for the structure factor. Okay? So the point I want to make is that if you have a lattice, there's always going to be a gap between the origin and the first Dirac delta function. That's extremely important. Now, extremely important in some sense, trivial in another sense, because it means that all not just a Bouvet lattice, which is the way, a mathematician will call a lattice one where you have one particle per fundamental cell, a periodic system where you have n particles per fundamental cell, otherwise periodically replicated. But whether it's a lattice or a periodic structure, you're always going to have a gap between 0 and the first Dirac delta function, which means all periodic systems with a finite number of particles in the fundamental cell are hyperuniform in a trivial way. Okay, so now this is audience participation time. Sorry to wake you up. So here you have a point pattern. Here you have another point pattern. One of them is hyperuniform. You have to guess which one. And don't say the right one. I've had that joke many times. Yeah, go ahead.
On the left. That's my guess.
Okay, turns out, it's a trick question, it's the one on the right. Actually, no matter how you answer, I'll say it's the opposite. No, it's not this one. But but what you do is there's a procedure, which I'll talk about in a little while, where you can make very tiny collective displacements, but not just randomly and sequentially. If you just did it randomly and sequentially, you would never arrive here. But when you do this collective, very, very tiny displacements, you get this. And this is not only hyperuniform, but there's a gap in the sense of a lattice that I showed you earlier. Okay? Yes, Joel.
There's an interesting result of Misha Soden, who was here last time. They proved in one dimension, if this S of k has a gap anywhere,
Yes.
then it has to be periodic. And they believe that it's true in higher dimension, but I mean really periodic.
Okay, so now that goes against what we have found. That goes against.
Well, in one dimension it's a theorem, so I don't think
Oh, no,
find anything against it. That the theorem could be wrong.
Okay.
How
But
are
it-
you making these points?
Oh, I'm gonna tell you. I'm gonna tell you.
In that theorem, is it a theorem about any distribution of points? For which
Which one?
It's a theorem in Fourier analysis. You're saying that if the
In one dimension, if you have a translation
translation invariant.
Yeah.
Okay, yeah.
That's the stationary.
and then if you have any gap, I mean, If for the hyperuniform,
If it's translation invariant, I believe. So
Well, of course, this is a finite system in a periodic box, so this technically is periodic.
no. This is for they talk
Right.
about an infinite system. No?
Yeah. Okay. All right, so just to give you, this is what I mean now by the way you normalize.
Okay, so what statistic is different in that last two? You said they are different. Tell us what the statistic is. You're saying it's this gap?
I'm going to show you that result. That was a teaser. I'm going to show you that result in a little while. Okay, so you have the scale number variance for 3D systems at unit density. And again, I don't want to dwell on the actual system, but these come from actual systems. I'm scaling the number variance by r cubed, right? So if you scale by r cubed for very large R, this has to vanish for very large R if it's hyperuniform. Okay? For a disordered system, this is just a constant, typical disordered system. For a disordered hyperuniform system, it has this particular behavior. And then if you have an ordered hyperuniform system like a lattice, you have small scale fluctuations that are occurring on the order of the lattice spacing, but then eventually this thing is decaying to 0. All right. Now I want to make a couple of comments just about equilibrium systems. So if you have a single component system in equilibrium at average density rho, this is a well-known expression from statistical mechanics. This is the number density, Boltzmann's constant, the isothermal compressibility. And then I'm denoting here a special symbol, asterisk there, to mean that it's in the grand canonical ensemble. And that's equal to the structure factor at 0, which of course is equal to 1 plus rho times the volume integral of H. So some observations. If you have any ground state, in other words, T is equal to 0, in which the isothermal compressibility is bounded and positive, it must be hyperuniform. This includes crystal ground states as well as exotic disordered ground states that I'm going to describe later. However, in order to have a hyperuniform system at positive T, so positive T, the isothermal compressibility, kappa T, must be 0. The system must be incompressible in this sense.
But what is this isothermal compressibility?
It's just the reaction to the reaction of pressure and density, the derivative.
Derivative of rho versus
The derivative of rho with respect to pressure times 1 over rho. Okay, well, I won't say anything about that. All right, so this is a very simple equation. I mean, everybody and their brother knows how to derive this equation. This is the number variance.
What is alpha 2 though?
I'm going to show you. This is the average number, okay? This is the volume integral of H, our familiar friend H.
Yeah.
Alpha 2 is a purely geometrical quantity. It's this. Take the common volume of 2 observation windows of radius r, the intersection volume, divided by the volume of a single sphere. Okay? So it's scaled in such a way that at the origin, when little r is 0, it has to be 1 because they perfectly overlap. Okay? And then as you go out, you have a cutoff when it's 2r. There's no common volume. And you can write this down in any dimension analytically. Okay. That's what it is. Now, I'm going to emphasize for a certain class of point.
So this is just a way of explaining how the variance goes with the pair correlation, basically.
Absolutely. It's determined entirely by the pair correlation. Entirely. Now, for a certain class of point processes in large R, we can show that you get this kind of an asymptotic expansion. Okay, so let's just look at the leading order terms. This is the term, the coefficient A, I'm going to call the volume coefficient because it's multiplying R to the D. B is the surface area coefficient. What is A? A is nothing more than the structure factor at 0. B is just a higher order moment of H. Okay, hyperuniform means, in this particular case, A is equal to 0, B is positive. Now, whenever you have that, you have this simple sum rule. So you can think of hyperuniformity as obeying a simple sum rule. That's the sum rule. Now, so this is the paper. I should have said it, and I don't want to gloss it over. This is the paper this comes from the paper with Frank Stillinger in 2003. Okay, so in that paper, this is the reason why we call this system hyperuniform and this one hyposurficial. Hyposurficial means that the coefficient A is positive where there is no surface area term. Now, it looks like that's kind of a trivial thing. For example, Poisson already meets that. But now, with some recent work with Roberto Carr, we're looking at amorphous ice. And we're looking at phase transitions involving amorphous ice. And it turns out, across certain phase transitions, we're finding that these systems are hyposurficial. The talk is not about hyposurficial. It's very weird. Yeah. Now, we'll see later that you can have, this goes to your question, Tom, you can have scalings in between these two. Now, it doesn't really matter whether or not you know what the Ornstein-Zernicke formalism is. Let's just take it, since everybody here is a mathematician, right? Take it as a definition. That you can think of H being divided into a direct part and an indirect part, okay? And the direct part is described by this function C. It's the direct correlation function. And in Fourier space, this is the way you define it. Now, for any hyperuniform system, H tilde at k is equal to 0 has to be minus 1 over rho. This is that sum rule. Okay, now look what happens to the denominator when that happens, when you have that condition. Blows up. And so that means C tilde of k equal to 0 goes to minus infinity, and then that means you can think of this state as being at a kind of a critical point, where instead of the usual, h of r is short-ranged in the sense that its volume integral does not blow up, and c of r is long-range. Well, anybody who knows normal critical point theories know that this is exactly the opposite. Everything is turned on its head, because in a normal liquid gas or magnetic critical point, h of r is long-ranged, okay, and c of r is short-ranged. So, a very simple observation, this is not extremely deep. For sufficiently large d, at a disordered hyperuniform state, whether you achieve it through an equilibrium route or a non-equilibrium route, it doesn't matter. You can think of this as having this kind of a scaling. C of r will have this kind of power law variation, where eta is going to be something like order 1, d is the dimensionality. And then this is what the Fourier transform looks like. It's this function that's diverging as k goes to 0. And as opposed to h, which is short range in the sense that its volume integral exists. So you see, notice the difference, d minus 2, d plus 2. And then s of k will behave like k to the 2 minus eta. Now, the reason why you introduce eta this way is to make contact with the normal notation that people use in critical point phenomena. Okay, now, one can think of a hyperuniform system as resulting from an effective pair potential at large R that is generalized, that is, I'm going to call it a generalized Coulombic interactions. Why? Because you can show, roughly speaking, you could show that the direct correlation function times with a minus sign behaves like a pair interaction, a pair potential, okay? And for large R. And of course, since C of R has this form, then an effective pair interaction would have this form.
I'm a little bit mixed up with all
Yeah,
the
sure.
notations. You got the H, you got the C, you got the C tilde.
Yeah.
Okay. So the C tilde is just the Fourier transform of the C.
Yes.
Okay. So that's not so bad. And the C is a kind of well, I mean, it's a I would call it a self-energy. Is it? I mean, if I look at it.
Well, I mean, you can think of it, the Ornstein-Zernicke equation normally is defined this way. If you think about it in direct space, like this, this is a convolution.
What you have there, the left-hand side?
H of R.
Okay. Yes. Okay.
And when you take the Fourier transform and solve, you get that equation. Now, the point I want to make is that long range, even though it's nice to have long range interactions to drive systems towards hyperuniformity, and a lot of systems that have long range interactions when they're in equilibrium will be hyperuniform. You don't need short range interaction, long range interactions when you have a non-equilibrium system. So for example, if I take spheres and I put them into a container and I shake them up and I jam them in some amorphous state, whatever that means, of course you can't have any more short range interactions than that, and that system is in fact hyperuniform. Now, another interesting thing to think about is instead of writing this in an ensemble setting, you can think about a single configuration. A single, very large point configuration in space. And now, instead of having an integral, I have this sum over this alpha 2. Well, that looks just like a pairwise interaction, a pairwise sum. And in fact, if you want to find the global minimum of the variance, it's equivalent to finding the ground state for this purely repulsive, compactly supported potential. For large R, then you can, in the special case of hyperuniform systems, you have this kind of a scaling, where now lambda of R, right, is just going to tell you about the small scale fluctuations. And what I'm showing here is the triangular lattice, this is actual data, of lambda of R, this coefficient, that's oscillating around some average value. And that's the quantity, that's the metric that I'm going to introduce.
So go back to that for just a second. So this is a triangle, this is a two-dimensional triangle lattice.
Yes.
Okay, and you're just looking at you're just showing us the fluctuations
in this surface term. That's it. I mean, it's not the stock market fluctuation, right? So it's a little more ordered than that.
R?
Yes, R.
So it's, you're counting the number of lattice points in,
Yes.
in the ball.
Yes, exactly. Exactly.
Counting R.
Absolutely.
I think Joel has a paper on that.
With Dyson.
Blätter.
Yes. Which yes, absolutely. So lambda bar is defined this way. So this is the average value. And if you have any kind of a lattice, then it's very easy to show that this is the case. Okay, you can write it down in terms of the Bessel function like that, squared. And lambda bar in particular, because it's the asymptotic coefficient, looks like this. So it's the sum. By the way, because I'm doing Fourier analysis now, this is in the dual space. Okay? So in the dual space, then I have this, you can think of it as an inverse power law potential. Now, I'm going to try to convince you that the surface area coefficient provides a useful way to rank order crystals, quasi-crystals, and special correlated disordered patterns. Now I want to make a statement about the Epstein zeta function. Well, the Epstein zeta function for a lattice is given by this. You can see that this is a general, this formula contains this as a special case. Okay? Now, this was something that when I was writing the paper, I learned from Peter. Now, for lattices, the minimizer of this guy when at d plus 1 is the lattice dual to the minimizer of the number variance. Okay, does that make sense?
No, I didn't catch that.
Okay. The minimizer of this for an Epstein zeta function.
As you vary,
For some S?
as you vary S.
Yes. In this particular case, I'm going to set S equal to d plus 1. I'm fixing S in this case.
It could depend on S.
But it could depend on S.
So
I mean, this is a generalization of Riemann, the Riemann.
you're minimizing. No, so
Look, this is like generalizing the lattice. If S goes to infinity, then you're looking for the lattice with the longest, shortest vector.
you're looking at you're looking at the
This is a
lattices. You're
smooth-
varying the lattices. Then.
Yes.
Yeah, this is a,
All right. Yeah.
the volume's always the same.
Yeah. Okay. Gotcha.
Now, for certain D, the minimizer of the Epstein zeta function is related to the optimal sphere packing. And Rankin, for example, showed that the triangular lattice was the winner. And then Peter is from Bergson.
You work on that, by the way, with this work of Marina Vyaskovia.
I'm sorry, say that again?
This lady who solved the sphere packing in 8 dimensions.
Yes,
and
of course.
in 4 dimensions.
Yes,
Vyaskovia?
yes.
Vyaskovia.
And then also Henry,
They generalized it. There are a few authors there.
yes,
They've extended that to show, for example, that the Leech lattice, we just proved this locally.
I know, I was going to say,
They've done it globally now.
I know. So Peter showed that locally in 4, 8, and 24 dimensions. And then these individuals proved in 8 and 24 dimensions.
Not 4.
No, 8 and 24 for them, but you conjectured in
the
4.
local, but their method is somehow.
So there's a local, you have a local.
It's an extent, if you ask which lattice has the longest, shortest vector,
Yeah.
that was proved by Henry Cohn and somebody some time ago, that's the Leech lattice. Locally, that was known by Genkov or somebody.
But you're perturbing locally within the lattice, within the
But
lattice.
now
Yes.
we're looking globally, they're
Yeah.
proving, they're using computer, but they're using this, their early work was using a computer. The new stuff is this major breakthrough by Marina.
Yeah.
And using that, they can extend, they can take potential functions which include this function with S arbitrary.
I see.
So you can take any S, so the Leech lattice is good for every single S,
I see, okay.
Yeah, that's.
which is remarkable.
Now, if you take so now I'm going to look at this metric in 1 dimension, okay? And not surprisingly, the integer lattice wins, and you can prove that the integer lattice wins. You have a disordered system that I'm not going to say anything about here. Then you have, I think most people will know what the Fibonacci chain is. You can think of it as the 1-dimensional quasicrystal, right? That's here. And then you have some other disordered systems. And as I said, we've done some recent work with Paul and Josh Sokolar and Erdal Ogus on quasicrystals, which I won't say anything about here.
The smaller this lambda bar is, the more ordered that we should think.
Oh yeah, absolutely. More ordered in the sense of suppressing density fluctuations. Now, in 2D, I already alluded to that result of triangular lattice. This is what the number, so that's the winner, okay? Then you have the square lattice, you have the honeycomb, you have the Kagame. Then you have,
Are we optimizing that?
this is this lambda bar.
These fluctuations that, you
Yeah, so I'm just computing lambda bar for different structures.
And if I have a lattice, what's lambda bar in terms of the lattice? Is the Epstein zeta function at a point or not?
Exactly,
Okay.
exactly right, D+1. Now, square, honeycomb, quasicrystal, this is Penrose. So Penrose, you can see, is much lower than these. Some of them are lattices, some of them are periodic systems.
higher,
What's that?
higher.
No, I'm talking about in terms of being the winner, it's higher, but it's less, what did I say? I don't know what I said. Okay, what I wanted to say was Penrose is ranked lower in the list. Okay, yeah. Now, and then you have disordered systems. Now, who wants to guess the winner in 3D?
3D, you mean if I take the same structure?
Same type of structures.
Yeah.
So it's not the face-centered cubic, obviously.
Peter knows it's not the space-centered cubic.
I asked the question.
It's actually, well, I gave the answer in the previous slide. It's always going to be the dual of what you would expect for the Epstein zeta function. So for the Epstein zeta function, it should be FCC, which means BCC for lambda bar, and that's in fact the winner. But look how little.
The differences, yeah.
Okay. Now you can carry out analogous calculations in high D, and we did this a number of years ago. And then, of course, one of the things that we had shown related to packings is that we think there are good reasons why we think that if you go to high enough dimensions, disorder wins over order in terms of the densest packings.
Do you have any evidence for that?
Not other than what we think is a strong conjecture, no, because it's impossible.
Some dimensions, this is not.
Well, in dimension 10, as Peter just indicated, we know that it's not a lattice. We know it's a non-lattice, and I think the number of particles in the fundamental cell is something like 40. Okay, something like 40. Yeah. Oh yeah.
That the best density of packing is not a lattice packing. Just that statement is known in some dimensions.
Do you know what is a status? I mean, Beck and forget what's the name, somebody else. They compared simple cubic lattice
Yes.
for the surface
Yes.
coefficient of the surface area thing.
Oh.
With compared to putting a point at random inside each cube.
Okay.
And there was,
Yeah.
and they found
Yeah.
a change, a transition around 800 dimension. I mean, apparently above 800, they were putting
Random
at
is better.
random inside.
You know, that's fascinating. I would love to get that reference. I'm serious.
Yeah, we mentioned it, if we had some correspondence.
But what lattice were they using? Is
The hypercube, just the hypercubic.
Oh yeah, no,
There's much better lattices in 800 dimensions. Minkowski shows that the random lattice has got a very long
Yeah.
shape and nobody knows how to make it explicitly.
it's a very long.
This is a remarkable fact. If you're in large dimensions, you can make a lattice of volume 1 whose shortest vector is about square root d, very long. Nobody has any means
Yeah.
of making that an explicit such lattice. You can show that a random lattice by averaging over all lattices something is true, but there's no explicit construction anywhere near it.
In fact, if you take the hypercubic lattice
That's the worst.
in dimension 10, it goes below Minkowski, lower bound. Okay, so I mean, I'm spending a little too much time on some of this basic stuff, but you have also a Fourier representation of the number variance, and I'm just going to skip to the three types of scalings you can have. There are three types of scalings.
Familiar with the recent work of Fordet Regev and somebody?
No.
Where the standard lattice is the best if you take the maximum over all balls. You don't take it at the origin. Then I think this was solved just recently.
You're telling me something I don't know. I would love to hear about it.
I found this very interesting, actually.
I'd love to hear about that, actually.
And it's quite an involved proof. Yeah.
So, you know, you have this, I call this class 1. This is class 2. You have a logarithmic term multiplying it. This is always the case. Look at alpha here. So if I look at the corresponding power law behavior of this, linear in K. You get non-analytic behavior at the origin. And then in between 0 and 1, you get this behavior. Now, a lot of the rest of the talk is going to be describing some specific examples of all of these. All right, now this to me, you know, I know there are experts in the room, but this to me just is so mind-boggling that you have this kind of, you have these results that if you look at the distribution of the non-trivial zeros of the Riemann zeta function, right, or the eigenvalues of random Hermitian matrices GUE, and less believable are the bus arrival times in Cuernavaca, Mexico. I don't believe that for 1 second. But it's a paper. Actually, Freeman Dyson, for some reason, believes it. He likes it. This is G2.
It's something that Percy Dack popular.
This is the structure factor. Linear in K. Okay, so this class 2 point process is always negatively correlated, such that's true, and the points tend to repel each other for small distances. This is all well-known stuff, but it's an example of a hyperuniform system, and as everybody knows in this room, Dyson mapped this problem to a 1D log Coulomb gas with this type of an interaction. The interesting thing to note is that if you look at GOE, which is what you get at a different temperature and still another temperature, GSE, they belong to class 2 as well. Now, constructing, so these are one-dimensional. If you want to construct and identify translationally invariant isotropic hyperuniform point patterns for D greater than or equal to 2, it's more challenging, but now we know many more examples. So physical examples, disordered classical ground states, fermionic point processes, which I'll say a few words about, maximally random jam states, ultra-cold atoms, this is other people's work, random organization, this is all other people's work like Paul Chaikin, Dov Levine, Daniel Hexner. These are non-equilibrium states. These are absorbing state kind of models. And you think about driving those systems to these non-equilibrium critical points. Vortex pinning and states in superconductors. There's a recent paper on the archive by Reichardt and company about this. This is actually related to the one-component plasma, this stuff. And something we call perfect glasses. Then you also have hyperuniform systems now that we're discovering in nature, not in Siberia, in a meteorite in Siberia, but in birds, in the eye of birds. The immune system, neuronal tracts. There are many other examples.
One thing you don't mention, which I'd never heard of until Rudnick and I were writing a paper about just points on the two-sphere.
Yes.
Something called Ripley's point pair function.
Yes.
Which is much older than you and
yes.
you're talking about. Why
yes.
is that not part of the language? That's a fair correlation.
If I remember Ripley, I think that Ripley function is related to. Yes, but if I remember correctly, if I remember correctly, the Ripley function is related to a function that Joel and Rees and company had looked at in 1959 in scale particle theory, which I think has to do with the probability of finding, what's that? Holes of a given size. I think. I mean, I'd have to look at it. I'm not sure.
Anyway, somehow he dug that up and we all our calculations Ripley.
Okay. You should have called them Joel functions.
I think this Ripley is a statistician.
Yes, yes, he was a statistician. Okay, so spin polarized free fermions.
And
So
what the function is the set of distances of pairs. You're looking at all, it's the point pair in dimension 2.
say that again?
The sum over all pairs of distances.
Yes.
So if you ask how many pairs of distances are less than r as a function of r for a point configuration.
Okay.
And if you Poisson, you can compute it. And,
yes. Okay.
And
I have to
there's a big theory about it. That's all I'm saying. It's got to be one of your numbers. There's no way. I mean,
yeah, I agree. I have to look at that because I have to look at that because that came up by coincidence a few weeks ago. Weird. Okay. Anyway, so if you take spin polarized free fermions, that's a natural generalization of the random matrices, right? Because if you're dealing with random matrices, you're going to be limited to basically one dimension or at the most 2 dimensions. A natural way of doing it is through these fermionic point processes, which I'll say a few words about. But anyway, in case 1, it reduces to the standard result, and then you can get it for any dimension, and this is what it looks like, and this is what G2 looks like. This is the scaling that you get. Okay, so in the same way that S of k goes to 0 linearly in k, you always will get in any dimension a scaling 1 over r to the d plus 1. That's the associated thing for large R in direct space. Now, one component plasma, of course, this stuff goes back to Genebra ensemble. A hyperuniform, and by the way, all of these come under determinantal point processes that I'm going to just say one slide about, is generated by a 2D one-component plasma, particles of charge E, interacting via the Coulomb potential immersed in a rigid uniform background of opposite charge. Sylvia and Sandler have a nice paper having to do with not disordered problems, but optimal solutions.
So
As
did they prove for general beta hyperuniformity? I meant to check on that.
not since the time she came to my workshop.
But
Not that I know about.
Did you know then that it was I mean,
Yes, she knew that as you went to t is equal to 0, definitely that they were hyperuniform.
But
I'm not sure. At positive temperature, that has to be a new result.
well, is it true?
Yeah, I'm gonna say it right here. I mean, Giancovici showed this.
Yeah, but that's beta equals 2.
Yes.
I'm asking for general beta.
General beta. Well, I think that there's a simple argument for it. I mean, Joel is one of the experts on this, but basically because of overall charge neutrality, you should expect it.
For beta less than 2, then
Yeah.
Certainly okay.
Yeah, and I think it's okay for, I mean, as far as hyperuniformity goes.
Right.
It should be true for all beta.
Should be.
I'm not following it. Are we in one dimension or two dimensions?
This is now 2 dimensions.
Yeah.
So you put charges. You
In the
put charges on a sphere,
sphere.
for example, and you have the log. You have your log potential with a beta in front of it. So that's it.
Yeah.
So we still don't know much about that system, by the way.
Yeah, but I think what Joel was saying, and I was agreeing with it, is that it should be true because of overall charge neutrality. Anyway, but here's an interesting thing that you
Overall
get.
Charge neutrality. Why? Because you've got your jellium in the background.
That's right.
To neutralize it.
Exactly.
And so jellium is. I mean, just because you have a jellium, you're okay.
Yes, exactly. Rigid background. Now, but the point I want to make about this is a really important point, fundamental point, is that the total correlation function goes to 0 exponentially, like a Gaussian. Okay? So everybody usually thinks if you have hyperuniformity in a system in equilibrium, you need to have long-range interactions or a long-range correlation. No, you don't. In this particular, I should have said correlations. You don't need long-range pair correlations, right? And in fact, because this is analytic, ridiculously fast.
Yeah, by the way, does anybody know of any other system except the two-dimensional case at beta equals 2, which goes faster than exponential? Do you know of any other?
No, I don't.
That's a question, in fact.
It must be a pretty fluky situation. I think that must be a very unusual situation. I mean, of course you could have it, but.
Well, anyway, I would be remiss if I just didn't say a few words about everything that I just said, the last 2 slides, can all be derived from determinantal point processes, okay?
Not beta's not equal to 2. Beta equals
No. I'm talking about beta is equal to 2.
Okay. But
But
not equal to 2.
I wasn't talking about anything other than what I had put on this slide.
Well, we were talking briefly about what happened.
Yeah, no, I meant anything that I had on the slide. By the way, but is that actually is that statement really true?
Yeah, I don't think they're not.
There are other special betas like in the random matrix.
Yeah,
They are no other. There's only 2.
I think that's all. I think they're not.
So they won't be determinantal.
No, I don't believe so.
Okay,
Yeah, no.
all right.
You're right. Am I right?
But
I
anyway,
think you're right.
But anyway-
I think it's fluffy and
to get the result that we got for the fermionic systems, we used a result of Costin and Leibowitz, which they provide a necessary and sufficient condition on this quantity H tilde to obtain a hyperuniform determinantal point process. All right. All right, so here's a conjecture that we had in 2003. It's a very simple conjecture. You have congruent spheres. We're going to have a packing of spheres, and it's going to be saturated, which means that there's no space to add another particle to the system. The conjecture is,
That's what that means. You can't put one in. I mean,
How did you start putting it? You're just in any position where it's now saturated.
that's right.
yeah. So that means that I can't possibly fit. I can't have holes where I can put something in.
Exactly.
But you're not. There's no randomness in this cycle.
No, this could be, I can imagine.
Just the configuration of.
Well, let me give you
Okay.
an example of a saturated packing, which is disordered. A saturated packing that is distorted is a random sequential addition. What you do is you have a box, put particles in randomly sequentially. If they overlap, you reject, until you find space, and you continue to infinite time. At infinite time, there's no space left to add another particle. That's a saturated packing, but it's not jammed. So the other condition here is that it's strictly jammed. Strictly jammed means that there are no collective motions. I can't shear the system. I can't compress the system. I have to go through this very rapidly. FCC, for example, is strictly jammed. It's a strictly jammed packing. I can't shear it. I can't compress it. Perfectly rigid. Okay, so we conjectured that all of these types of packings will be hyperuniform. And then, remember...
But saturated is not enough.
No. It's definitely. Because RSA, in fact, remember that audience participation example on the left? That was RSA.
What's RSA?
Random sequential addition.
This means something to us.
It's not the stuff that is used in cryptography.
It's
Yeah.
cryptos,
Yes, it's not that one. Yeah.
Maybe that's good too. I don't know.
Anyway, so if you take what we call maximally random jammed, meaning it's maximally random according to some kind of an order metric, pick lambda bar if you would like, subject to the condition that it's strictly jammed.
So is this, if you do this random RSA, what you say? In 3 dimensions.
In 3 dimensions, it would not be.
You arrive at the maximum packing, you arrive at another number, right?
That's right.
Like 60%.
It turns out 55 in 2 dimensions and 38% in 3 dimensions. No, you can only do that numerically. Renyi solved the problem for the parking problem in 1 dimension, exactly. But in higher dimensions, there's no solution. There's no exact solution. Anyway, so this is a 1,000,000 particle packing, and you have to, numerically, it's difficult to assess whether something is hyperuniform because you have to get the smallest wave numbers, right? And you're always limited by the system size. But to the best of one's ability here, our ability, we determined that this was linear in K. And of course, this is to be contrasted with hard sphere fluids. So the hard sphere fluid, along the stable branch, you have exponentially fast decay of correlations. And that has to do with the fact that it's really an analytic function at the structure factor. It's analytic at the origin. Whereas this, of course, comes with a power law decay like this.
That's numerical also, you don't know for the hard sphere fluid, that you have exponential.
Yes, that's all numerical. Absolutely.
What's a hard sphere fluid?
Equilibrium hard sphere is a Gibbs ensemble.
Ball, hard ball.
What do you mean by hard sphere fluid? Anything that's not close packed or what?
No, anything, so you have a phase, and as you increase the density, there's a stable fluid branch, which we disordered branch. Then you have presumably a first order phase transition. I know that's a problem that Joel has been interested in proving. There's a first order phase transition, and then you go to FCC. But anyway, this apparently is, at least numerically, a universal feature for any packing that's maximally random jammed. You can have polyhedra, you can have ellipsoids, you can have truncated tetrahedra, whatever you want, and you seem to get this. So it's a signature. It seems that the linear behavior is a signature of these MRJ states.
Got everything. We got hard balls and we got super balls.
Oh, you know what a super ball is.
I mean, when I was a kid, there was something called super patty.
And you vary this exponent, p.
That's what it is.
That's all it is. And you can write it down in any dimension. Okay, I have a chicken. So, the interesting thing, optimal sampling of light, there are theories that say the best way to sample light is if you have different cones. I think everybody understands the way photoreceptor cells work. Humans have 3 types of cones to detect color, right? And so the best way to sample the light is to think about a nice uniform decoration of the triangular lattice with the 3 types of cones. Now, that happens in some species. So presumably in these animals, it's the optimal. Birds are highly visual, yet their cone photoreceptor patterns are irregular. And there was an animal vision expert who came to me.
Where do we fit into this picture?
Excuse me?
Where do we fit into this picture? Where do I read
Oh.
retina?
Yeah, you're going to steal my punchline, though, if I tell. Okay. I'll pretend I didn't hear that. Any, any, okay, so this animal vision expert, who's a PhD medical doctor, came to me. He had beautiful data for the eye of a chicken, right? And people always ask me, does it matter whether it's a chicken? And I said, it only matters because it's easier to kill chicken than eagles, for example. But outside of that, it doesn't really matter. So this is going to happen in all kind of birds. So this is actual data. They have 5 cone types, okay? So think of the blues as...
Seriously, what is this data of? You have all these pictures, I don't know what you do.
Ah.
So we have a bird, we have a bird's eye, what is it doing?
We have a bird, the retina of, so in your retina you have these cones that you can think of sitting on a,
So these guys actually go to the retina and see this kind of pattern?
No, these are on your retina. These are the photoreceptor cells that are actually part of your retina that enable you to detect light.
Behind each one of the little retina, you have a, I guess you have a...
Yes.
that
Behind that, of course.
tells you what kind of color you're seeing.
Yes, exactly. So for example, blue, right, is going to detect blue and you know, part of the spectrum around blue, and red, part of the spectrum red and around red, and so on.
And what about the black and whites? You don't have that? They're not...
What do you mean black? Oh, you mean the rods?
yeah.
That's for night vision.
But they're there too, right?
Yes, yes. But here, of course, you know, he's a good experimentalist. He's only showing us, he's only highlighting the photoreceptor cells.
But if you're thinking of what the structure of this thing is, doesn't it matter the relative susceptibility of each receptors? Because those are different.
What do you mean the susceptibility?
That so I don't know about chickens. With human eyes, the green receptors are actually more susceptible. There's a higher probability that if you send one green photon on a green receptor.
Oh, now you're getting into a realm that I have no,
No.
you're beyond me. You're beyond my vision. Anyway, one of these actually is if I take the centers of these things and I exaggerate their sizes, this is real data. And another one is actual computer simulation data from our group. Now, not surprisingly, as Peter immediately captured.
So it's not the same 2 pictures as you showed previously?
No, completely different.
He's the fast learner, he gets the right one.
But he also detected that it wasn't the same picture, which is also... okay, but here's the thing that's really weird about not surprisingly, as Peter guessed, the violet species, the green, the blue, and so on, you have 5 different types. This is the structure factor. You can see they're all going to 0 for small k. And then the entire population, if you looked at all of them without separating them out,
Population of what? You mean you just...
the whole thing, the entire,
No colors.
all of the colors together, if I treat all of the points equally,
all equal weight.
all equal weight. Now, this we call multi-hyperuniformity, because if I gave you a distorted point pattern and I said, remove a subset, a significant fraction, such that what remains is hyperuniform, that's a highly non-trivial algorithm. Yet the bird has that solution. It's remarkable, so we call this...
The subsets which are of a fixed color.
Exactly. Exactly. Well, it looks like I'm not even going to be able to get even halfway through the talk. But I want to just say a few words about these disordered ground states, which I think are fascinating because it gives you exquisite control of the structure factor. You can create disordered classical ground states, and this actually goes to Joel's original comment, which I would like to know a little more about that theorem. So typically you take a liquid, you cool it slowly, it undergoes a phase transition, then you go along a crystal branch, and as you go to t is equal to 0, you get something as a ground state that typically is periodic with high crystallographic symmetry. That's our normal experience, like ice, right? Imagine doing something like that, except when you go to t is equal to 0, you arrive at something that has no symmetry, okay? It's disordered in the lowest energy state. So the way that we describe this is we describe it, the procedure as a collective coordinate procedure, and it's inherently a Fourier setting, inherently Fourier setting. So imagine that you have n particles with some configuration in some fundamental region under periodic boundary conditions with a pair potential V that is bounded with some Fourier transform. Now, the total energy is nothing more than that in direct space, but because of the setting under periodic boundary conditions, I can use Fourier analysis and I can re-express this like this as a sum over vectors in reciprocal space, v tilde of k, structure factor plus some constant that doesn't depend upon the structure. Okay? That's really an identity.
So you're constructing them by choosing the right Fourier transform for your potential, is that the idea?
Yeah, exactly. In fact, what I'm going to do is I'm going to prescribe the Fourier transform. And then I'll worry about what the direct space is. In fact, so what you do is you say, okay, look, v tilde, I'm going to say is positive inside this gap. So this is why Joel's comment before was pertinent. And then it's 0 otherwise. So for example, take a step function. If I have an algorithm, an optimization algorithm, in which I can move the points, so I can relax the system, I move the points in such a way that at the end of the process, the structure factor is 0 where this has support, okay? Then you can see immediately that that has to be the ground state. Is that clear?
No, but
Because this is 0 where this is positive, and this is positive where this is 0. And then you're left with some arbitrary constant that has nothing to do with the structure. Now, the Fourier transform, to get back into direct space, has this Bessel-like behavior, which, but it's long-ranged. Now we're going to call these types of systems, when they exist, we're going to call them stealthy, because throughout all of these wave vectors, there's no single scattering events. So it's transparent, if you will, to single scattering events. So we call them stealthy. Now it turns out the stealthy ones are generally going to be highly degenerate. The ground state structures are going to be highly degenerate. The way you can tune what you get is through a dimensionless parameter chi, which is going to be the ratio of the number of constrained degrees of freedom, which means how many wave vectors you're going to be setting the intensity to be 0, to the total number of degrees of freedom, which is basically d times the number of particles. So in Fourier space, it looks like this. There's a region, this is in 2 dimensions, up to capital K, where there's no scattering event. There's nothing. You've forced it to be 0 here. And it's unconstrained outside that. Now, one class of stealthy potentials has a power law form like this. So this is just a step function, Heaviside step function. So you cut off there at capital K. Then it has this kind of power law form inside So you can generate things like this, and then in direct space, they look like this. Depending upon what the exponent is, you get a pair potential that, and in this case, I think, well, anyway, I think this is 3 dimensions. You get this kind of power law behavior for large R.
So I'm getting a little lost here. So what do you get in the end? Because we're running a little over time.
Yep. I'm going to tell you immediately. So you get disordered ground states. If this dimensionless parameter chi is sufficiently small, then
What is chi again?
it's the ratio of the number of degrees of freedom that you're constraining, the constrained degrees, divided by the total number of degrees of freedom that you have. Okay, so the point is that you get disordered ground states. This is a small chi value. And by the way, these are stealthy systems. And then this, you've increased chi to a point where now you're introducing also short range order. And then at some point, if you make chi too big, you get crystallization. You have a phase transition to crystal states. And then the ground state manifold is really overwhelmed by the crystal ground states. All right. Anyway, there's a theory for this, and basically the theory is that you can think of these as hard spheres in Fourier space. And the reason why is because the structure factor, let's take a particular limit, looks like the step function.
So this is all done with this structure factor, right?
Yes.
And then this additional chi constraint.
Exactly. But then you can write down a theory that says that these are equilibrium, you can think of these as equilibrium hard spheres in Fourier space, and then you could apply the machinery of hard spheres, which Joel has done a lot of work on, but in Fourier space, okay? And then you get all of the expected results. So for example, you compare it to simulation, and this theory that's based upon hard spheres in Fourier space look like this. And you can see that the agreement is really quite good. Anyway, there's a bunch of other things which, obviously I didn't get a chance to finish, but that's all I'll tell you about.